Counting with identical items. So far, we've discussed counting arrangements in which each of the n items is different. This is natural when the individuals are human beings, something like that. Sometimes we have to arrange sets in which some of the items are identical, and this requires a special approach to calculations. So consider this problem. Pause the video and work on this for a minute. Okay, a librarian has 7 books to arrange, 4 different novels, and 3 identical copies of the same dictionary. In how many different orders could these 7 books be put on the shelf? Think about it this way. Suppose we temporarily treat the 3 dictionaries as 3 different books, D1, D2, D3. Then we could put the 7 books in 7 factorial different orders. Now let's think about those arrangements. Here's a typical arrangement, and I'll just say that J, K, L, and M are the 4 different novels. So J, K, and L, M are scrambled in some order, and then the 3 dictionaries are in there. Now consider arrangements with the 4 novels in the same place and just the 3 dictionaries in different places. How many different ways could we rearrange just those 3 dictionaries? Well, there'd be 5 other ways, a total of 6 different arrangements. And of course there would be 6 different arrangements because there are 3 dictionaries and 3 factorial is 6. So we have 6 ways to arrange those 3 dictionaries, and everything else stays the same. Well, now we were temporarily treating the 3 dictionaries as if they were different, but really they are the same, and all 6 arrangements on the previous slide would result in an identical arrangement of books on the shelf. Because in fact, if the dictionaries are identical, changing the order of the dictionary doesn't matter at all. Of the 7 factorial total arrangement, that would be an overcounting. We could group them 6 at a time into groups like this, and all 6 in the group would result in an identical arrangement of books on the shelf. So the number 7 factorial is 6 times too big. So we'd have to do 7 factorial divided by 3 factorial. And of course what we could do, we could cancel the 3, 2, and 1. Then when we multiply, we cancel that, we get 7 times 6 times 5 times 4. 5 times 4 is 20. 7 times 6 is 42. 42 times 20 equals 840. There'd be 840 different arrangements of the 7 books. Notice that in a set of n items, there were b identical items, and the total number of arrangements is n factorial divided by b factorial. That's a very important idea. Suppose the collection of n items contains more than one set of identical items. For example, of the total n items, there could be one group of b identical items, a different group of c identical items, and yet another group of d identical items. You could imagine that we had so many identical dictionaries, and then so many identical copies of a particular play by Shakespeare, and then so many different copies of the same novel by Faulkner, that sort of thing. So different streaks of identical items within the whole set. Then the total number of arrangements would be n factorial divided by the factorials of all those individual groups, b factorial, c factorial, d factorial. And that is how we calculate the total number of arrangements. Some sources call this the Mississippi Rule because of its application to this question. How many different arrangements can we make of the 11 letters in the name of the U.S. state Mississippi? And of course, what's special about the U.S. state Mississippi is that it has so many repeated letters. It has 4 S's, 4 I's, and 2 P's. So it turns out that if we wanted to figure out the number of arrangements, it would be 11 factorial divided by all those individual factorials. 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. Now we're not going to calculate this right now, but that is how we'd apply this. In other words, dividing the total number of factorials by the number of repetitions in each particular group. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we have 5 different identical copies of one book and 2 identical copies of another book. And so that means that the total number is going to be 8 factorial divided by the product of 2 factorial times 5 factorial. Well, we'll cancel the 5 factorial first. Expand the 8 factorial, expand the 5 factorial. Of course, we can cancel a lot right there. Whenever you have factorial over factorial, there's going to be a lot that you can cancel. And then we cancel the 6 and the 2, so we get a 3. 7 times 3 is 21. 8 times 21, well, 8 times 20 is 160, plus 8 more would be 168. So there are 168 distinct orders on the bookshelf. Here's another practice problem. Pause the video and then we'll talk about this. Now this one is a deceptively difficult one because you might want to get wrapped up in all kinds of formulas and this sort of thing. This is actually a problem that punishes people who want to use a formula, because it turns out it's much easier simply to count. So let's think about this. Let's think about different categories. First of all, could we have 3 all of the same color? Well, we definitely could have 3 greens and 3 blues, but we can't have 3 reds because there's only 2 identical reds. So there's only 2 arrangements that are 3 of the same kind. Now we'll look at the ones that are 2 of one color and 1 of another color. So we could have 2 greens with either a blue or a red, 2 blues with either a green or a red, and 2 reds with either a green or a blue. So there are 6 possibilities there. So 2 possibilities in the first case, 6 possibilities in the second case, and then finally we could have 3 different colors. Well, there's only one way to do that. We'd have 1 green, 1 blue, and 1 red. And so that would be 2 in the first case, 6 in the second case, 1 in the third. 2 plus 6 plus 1 is 9. There are 9 different possibilities. If in a total set of n items, b items are identical, then the total number of distinct arrangements is n factorial divided by b factorial. If in the set of n items b are identical, a different c are identical, and a group of d are identical, then the total number of arrangements is n factorial divided by the product of all those individual group factorials, b factorial times c factorial times d factorial.